Perhaps let's get started. My name is Frank Slazer. I'm the president and CEO of the Coalition for Deep Space Exploration. Coalition's an industry trade association. We represent about 50 firms from around the nation focused on space industry issues, space exploration, space science, and space technology development. Our membership includes the most diverse range of companies in the industry, from established aerospace prime contractors and newer commercial space entrants to a variety of small companies in the industrial base. Our membership spans that industrial base, and 46% of our members are actually small businesses, and nearly 10% are composed of women-owned or veteran-owned companies. This is the 5th episode of our Space 101 educational webinar series, where we bring space experts from industry and government together to help educate the media on how space missions are accomplished, what goes into space system design, and what is the science behind what we do and what we want to do. This webinar will be archived on our website along with earlier episodes and is available to you for subsequent viewing, or if you want to refer this content to your colleagues. Today's episode, Mission Architecture 101, we'll look at what goes into space mission design, specifically those missions associated with NASA's Artemis human space exploration program. Our moderator, Kristen Kapovic, is the Coalition's Director for Strategic Alliances and Operations. Kristen, over to you. Kristen?
You are muted, Kristen.
Sorry about that. Amateur mistake there. Good morning. Thank you all for being with us today on this rainy Friday in DC, being with us virtually. We're excited about this. I think this may be our best one yet. We've got some real giants in the space industry who are going to be here today and speak with us. We hope this will be educational. As Frank said, this will be recorded, and I don't think he mentioned, as per the past ones, but if this is your first one, we'll be doing questions on chat. Just to keep things smooth, everybody should be muted, but feel free to jump in at any point and ask questions on chat, and then I'll be going to our speakers at the end, and we'll make sure to get to your questions. We should have 30 to 40 minutes of presentation and then plenty of time for Q&A at the end. So to introduce our speakers here this morning, we are honored to have first Doug Cooke, who I should note is on the Coalition's Board of Advisors. So he's no stranger to the Coalition, I'm sure no stranger to many of you. He's currently an aerospace consultant with over 48 years in NASA programs. And during his 38 years at NASA, which included Johnson Space Center and headquarters, he held senior leadership responsibilities with achievements during critical periods of the Space Shuttle, International Space Station, and Human Exploration Spaceflight programs. After 4 years as the Deputy Associate Administrator, he then served as the Associate Administrator of the Exploration Systems Mission Directorate at NASA headquarters for 3 years before retiring in 2011. In this role, Cooke was responsible for leading the development and integration of flight hardware systems for future human space exploration beyond LEO, including Constellation, SLS, Orion, and ground systems development and operations. And as I mentioned, he's also on the CDSC Board of Advisors. Next, we have Dave Burke with Boeing. He's Boeing's Director of Business Development for Deep Space currently. He's also an Air Force veteran whose career has encompassed a broad spectrum of projects, from DoD shuttle missions and launch vehicle guidance systems to space physics at NASA headquarters and national security satellite systems design and development. In his tenure at Boeing, he has served as one of Boeing Satellite Systems chief engineers and a department manager with responsibility for integration and launch of Boeing satellite systems worldwide. We're also joined today by Mike Sarafin of NASA. He is currently the Artemis mission manager at NASA headquarters for the upcoming missions to return the US to the moon. In this role, he served as the mission management team, he serves currently as the mission management team chairman for uncrewed and human space missions, including the Artemis program, comprised of the Space Launch System, Orion spacecraft, and launching from the ground systems at the Kennedy Space Center. Prior to this role, he was a NASA flight director for many years, leading human spaceflight operations, where he led 64 human spaceflight missions, including 43 shuttle missions and 30 International Space Station missions. So for the sake of brevity, we've shortened these bios. All of these gentlemen have won many awards, many accomplishments in the space industry, and we're very excited to have you today. I want to start things off here, and I'm just going to be moderating questions to try to keep things moving along, but we want to leave most of the time for our panelists to speak. So I want to get started with Doug. Can you kick us off by discussing some of the key considerations that are taken into account when planning for sustainable mission architecture to go to the moon and beyond?
Yes, thank you. If we could go, what is it, third chart that addresses what we've done through in the development of where we are now with let's go back one, please. In developing an architecture and a roadmap. We can go back one more to the previous chart. I think it's 3. Yes, that's it. As we got into developing the roadmap and architecture initially, and this is, I speak from the time that I was at NASA and we began the Orion and SLS programs. We had gone through an extensive effort of developing objectives that would lead to requirements, and looking at the roadmap for in the first place going to the moon and then to Mars, looking at objectives. What do we do what are we going to achieve when we get there? And for the moon, we had a big workshop in 2006, and it led to objectives in areas of gaining scientific knowledge, understanding what could be done in developing resources that could lead to commerce, what we could do in preparation for Mars on the moon, looking at global partnerships and doing all this, and understanding the benefits to society. So those led us to some of the blocks at the bottom of this chart. I wanted to put on this chart today's best understanding of objectives are found in the Lunar Exploration Analysis Group, who has a lunar roadmap that is kind of built on what we did back then and is really a good set of objectives, I think. And I think they continue to develop that. It is led by both that group and the MEPAG, which is the equivalent in the Mars program. Those are led primarily by science folks, but they do embrace all of the objectives, including the things I mentioned, not just science, but also the exploration objectives and in situ resource utilization and so on. So they I would say, maintain a really good handle on that today. In terms of considerations and requirements, we looked at performance, obviously. In going beyond Earth orbit, you're propelling a lot more equipment for human space flight than we necessarily do on a given mission to low Earth orbit. So we looked at mass beyond Earth orbit. We were interested in payload volume too, because some of these flight elements would be large, things like HABs and rovers and things like that. We also looked at risk associated with the mission and tried to minimize the number of flights and critical operations to reduce risk. We, at the time of that we decided on the design for a space launch system in 2011, we also looked at what was existing. What are the propulsion technologies that we had in hand? We had already tested a 5-segment solid rocket booster. We had shuttle main engines that we could use when the actual engines for the first engines for SLS from the shuttle program. It turns out we looked at kerosene engines, but the U.S. had not built a big kerosene engine since Apollo, and that would have been a technology development. So our best technology was in the area of hydrogen oxygen engines in the space shuttle engine. And I should say that in heritage hardware that we had, these had been maintained and the technologies improved over the life of the shuttle program. So that's really kind of where we went there. We also were interested in looking at industrial base and its health. We looked at expediency in moving on because we had a lot of people working at the time we started this and wanted to get on the path as soon as possible. We can go to the next chart. So as we develop these requirements based on all these considerations, we came up with basic elements that we would need to satisfy the objectives and do the missions on the moon. Can we have the next chart, please? There we go. So over many years of working exploration, going back over 30 years, we had found always that the first critical elements in getting humans into space beyond Earth orbit was development of a heavy lift vehicle based on performance needs. Importantly, in that we needed efficient in-space propulsion and we needed a crew vehicle. But the crew vehicle and the launch vehicle were the first critical steps. And they were needed, obviously, to transport the crew, but also to transport large elements such as HABs, landers, rovers. We needed also EVA, obviously, for the surface, which we had not done since Apollo. So the requirements led to our understanding of what we would need to go to the moon in the initial cases, and then to Mars later on. Next chart, please. So I mentioned risk a little earlier. One of the things that we looked at for years, and this is actually an old chart, it goes way back, and we've had different versions of it over the years, but it's important in going to the moon and especially in going to Mars, because if a single Mars mission, the mass is on the order of the mass of the current space station. So it was important to us to understand risk. And on this chart, the blue line shows the number of, actually it shows the mass lifted versus numbers of flights. And as you increase numbers of flights, as the mass that you lift gets lower, your probability of mission success goes down. And this is a simple calculation of probabilities. If your rocket launch system is 98% confidence in terms of probability of success, if you have 2 launches, it reduces your mission. Your mission risk goes to about 96%. The more launches you have, and I have, I think, 0.98 12 times. If you have a lot of launches, your mission success rate goes down with the probability calculation. So this was factored into the size of the launch vehicle that we were going to build. We had arguments early in the 2000s and earlier than that, for that matter, of, well, we could just launch it on EELVs, but the risk factors into that in terms of numbers of launches, as well as the mass goes up because the interfaces between components is basically a tare weight that you have to add. It actually increases mass of the overall mission. So these are important considerations in developing the requirements that led us to where we are. And Kristen, I think I hand it over to you at this point.
Yeah, thanks, Doug. That was really, really helpful. Next, we want to take a look at some of the basic differences between deep space and near Earth environments and how those considerations influence the system architecture. So I think first we want to turn it over to Dave, and then Mike, and then back to Doug.
Okay, Leslie, next chart, please. So this is just kind of giving an overview of what the Earth-Moon neighborhood looks like. So one of the things to remember as we're, it's our destination, at least the near-term destination, is to go back to the moon.
And one of the things to think about is that, the Earth and the Moon, we kind of think about we're sitting here on the Earth and the Moon is revolving around the Earth, but actually they're kind of revolving around each other. So this is actually a depiction of, I'm going to take you a little bit into Einsteinian graphics, but it actually, at least for me, helps me think about what's happening with gravity with a couple of bodies in space. So you'll see there a two-dimensional depiction of a three-dimensional gravity well. And the Earth and the Moon are actually rotating around each other. So if you think about it, the Moon is about a sixth the mass of the Earth, and so it's kind of like if you were swinging a child around, and you'd have to lean back and you'd be going around each other as opposed to one going around the other. And then what you see here, there's when you start looking at that, there ends up being 5 points, and we call libration points or Lagrangian points for the guy who originally came up with them. And those are points where you actually have where gravity is kind of neutral in those areas. So the easiest one to think about is the L1 point. And so the L1 point is just the place where the Earth's gravity and the Moon's gravity cancel each other out in between. And I won't go into explaining the others, but they're really kind of important from the standpoint of what we're going to be doing with the Artemis missions, because we're using these Lagrangian points and not just going back to low lunar orbit like we did with Apollo. We're going to use those Lagrangian points to do some more interesting orbits around the Moon. And now I guess I'll turn it over to Mike to talk about some of the other aspects of the Earth-Moon environments.
All right, thank you, David. If we go to the next chart, please. So in order to execute a mission and safely fly our spacecraft in the deep space environment, or to get from Earth out to the Moon and back, or to sustain our astronauts for an extended period of time, we need to take into account the deep space environment and the environment that we're going to fly through as part of the architectural design. I will note a couple of points here that the low Earth orbit environment is dramatically different and than the deep space environment. And the deep space environment is significantly harsher than low Earth orbit. And a few examples of that are when you're in low Earth orbit, the spacecraft and any astronauts flying on board are afforded the luxury and protected by the Earth's magnetic field, or the magnetosphere. And when you get outside of that magnetosphere, you're in the deep space radiation environment, where you're exposed not only from a spacecraft and avionics standpoint, but also the humans on board, to galactic cosmic radiation and particles and ionized radiation from the solar wind. So in order to leave low Earth orbit, we need to, and to fly missions out to the Moon, we need to fly out through the Van Allen radiation belts. There's an inner belt that ranges from about 1,000 to 8,000 miles from the surface of the Earth, and then an outer belt that ranges in distance from about 12,000 to about 25,000 miles from the surface of the Earth. And these are areas where these high energy particles are captured and in higher concentration. So we have a mission going out to the Moon. We got to go through both of those radiation belts and out into that deep space radiation environment. Then also, to return our astronauts home, we got to fly back through that. So any missions, again, out to the Moon need to take that into consideration. But there's also another factor that is not shown specifically on this chart, but I will highlight as well, which is the micrometeoroid and orbital debris environment. So humans, over the course of the spaceflight programs, have put a significant amount of orbital debris, man-made debris, in the area that extends out to about where the Van Allen radiation belts end, which is coincident with about geosynchronous orbit. And there's high concentrations of debris or dead satellites or just other objects out there that in order to depart the Earth and get out to the moon, we need to pass through. But once we're outside of that environment, we enter into the micrometeoroid environment, which is not as well characterized. We can track stuff that we know we've put up in orbit, the orbital debris, but the micrometeoroid environment is largely just a known risk that is not as well characterized. So again, our architecture needs to account for these factors as we fly from low Earth orbit out into the deep space environment, and they are different environments. So with that, I'll pass it back.
I think we had next slide, and I think Doug, you were going to cover that.
Yes, this is just a simple analogy in terms of some of the differences in going to Earth orbit and going beyond to Moon or Mars. So the analogy being that if you're gonna move a short distance that's 3 miles away, you might use a truck, and if you're going to go and if the ISS were 3 miles away and the moon would then be 2,500 miles away, like cross country, you would go to perhaps go to larger lift capability as in a large airplane. An analogy in my life is when I was traveling or moving between houses and different neighborhoods, I'd rent a U-Haul, and when we went from Houston to DC years ago, we used a moving van. So it's a matter of volume and the number of trips that you make to get the job done. So it's just a simple analogy, actually. Give it back to you.
All right, yeah, Doug touched earlier a little bit in one of the first slides about the physics, but I want to look at that a little bit deeper about the physics of going to the moon and orbital dynamics, which impact our considerations. So Dave, I think we want to go to the next slide and turn it over to Dave and then Mike.
Okay, so yeah, I'm going to do the easy slide here, and then Mike's going to do the more difficult one. So I'm going to take you guys back to your high school math class, and at least that's where I learned about some of this stuff. And there's a thing called conic section. So if you remember, there's a cone, and then if you bisect that cone, you end up with different shapes, and the shapes that you end up with are either ellipses or circles or parabolas or hyperbolas. And that's essentially what's happening when you're doing orbital dynamics. Everything is really made up of those different shapes. That's how your spacecraft is going to move around in space, is based on those kinds of shapes. So, and if you look at it, they're all kind of variations. You start with the thought process of an ellipse, and the bottom part of the ellipse, the thing that's closest to the object that you're orbiting, is called the periapsis. And if it's the Earth, it's the perigee. If it's the Sun, it's the perihelion. It's all the Greek terminology for the parts of the word. So and then as you go, I'll go next chart. As you start looking at that, how do you move from one place to another in space? If you fire your engines at apoapsis or apogee, it raises your periapsis, and it actually makes it more circular. If you fire your engines at periapsis, it raises the apoapsis and makes things more elliptical. And as you keep going, essentially you go to a larger and larger ellipse until that ellipse opens up and becomes a parabola. And as that parabola, essentially a parabola will take you to an escape orbit. So if you look at down in the lower left, that parabola, doesn't go intersect itself again, right? So as soon as I hit that kind of a shape, put enough energy into it, raise my apoapsis high enough to hit escape velocity, then I keep on going on a parabola. if I keep on putting energy into that, I end up going into a hyperbola. So, and those are the escape trajectories, and it just depends on how much energy you put into the system. I'll turn it over to Mike, and Mike's going to go in a little more difficulty and talk a little bit more about the gravity wells we teed up earlier.
All right, thank you, Dave. If we go to the next chart, please. So we'll talk about how that applies to the Earth and the Moon system and the gravity wells that we know that we have to deal with. Before we do that, we'll talk about the different types of energy. There's kinetic energy, which is really a function of speed, and then there's potential energy, which is stored energy. And when you want to think about potential energy, if you look at the gravity well around the Earth or around the Moon, the higher you are away from that object or the body, the Earth or the Moon, the more potential energy you have. Kinetic energy is really just how much speed do you have. So if you're looking at a suborbital trajectory, that is a low potential energy trajectory, but it has a certain amount of kinetic energy. When you look at an orbit about the Earth or about the Moon, you have both potential and kinetic energy. And then you have, when you achieve Earth escape, you actually have enough potential energy to escape that particular gravitational field. And as David referenced earlier, the Earth has a gravitational pull that is 6 times the Moon. So in order to get out of the Earth's gravitational well, we've got to overcome the gravitational acceleration, which is 32 feet per second, and get over to the Moon's gravitational field, which is about 5 feet per second. And the difference between the Earth and the Moon is not only in terms of force and acceleration or the gravitational pull, but also the Earth has an atmosphere about it. So we've got to overcome the atmospheric drag, which is a problem on launch phase and ascent, but it actually works in your favor on return and descent. And we'll highlight that more here in a few minutes. The Moon really has no substantial atmosphere, so it really doesn't work for you or against you. But in order to conduct a mission that would go from the Earth to the Moon and then back, we need to launch and have enough potential energy to escape that gravity well, and through what's called the translunar injection maneuver, transfer from the Earth's gravity well over to the lunar gravity well. And through that translunar injection maneuver, you literally target the Moon's gravity well, or in the case of a science mission, target another orbiting body's gravity well. And then you can enter into any number of orbits, a low lunar orbit or a high lunar orbit. You execute your mission, and then when you're ready to return, you have to have enough performance to escape that gravity well and then retarget the Earth's gravity well. And then when you come back into the Earth's gravity well, you can use now that atmospheric drag to slow you down, and that actually works to your advantage. So if we go to the next chart, please. This is an example of how our program of record, which is our Space Launch System and the Orion spacecraft, use specific capabilities to achieve that transfer of energy to go from the Earth to the Moon and back. So the Space Launch System, if you work your way from the lower left to the upper right, has various performance capabilities in the form of the solid rocket boosters, which produce about 75% of the thrust to overcome the Earth's atmospheric drag, plus the Earth's gravitational pull, in combination with the liquid core stage in the RS-25 engines. The core stage stores that chemical energy as well as the boosters, converts it into potential and kinetic energy that gets you into Earth orbit. And then the upper stage, in this case, the interim cryo propulsion stage with the RL-10 engine, then has chemical energy again stored in it that allows you to transfer out of the Earth orbit and into the lunar orbit by means of the translunar injection maneuver. The interim cryo propulsion stage then pushes the service module and the crew module that you see here, which at that point, at the point of translunar injection, is about 58,000 pounds in mass, and sends it over to the moon. And the service module then performs a braking maneuver using a smaller rocket engine, the Orion main engine, and the chemical energy stored in the service module to enter that smaller lunar gravity well, conducts the mission, and then when it's ready, fires the engine again through a series of maneuvers that David described earlier that allow you to escape the lunar gravity well, and then on a trans-Earth injection maneuver, return back to the Earth. And then when you come back in the Earth's atmosphere, that capsule with our astronauts inside of it has a heat shield on it. And we'll talk more about this later, but that heat shield uses atmospheric drag, but also protects our astronauts when they come home. So with that, I'll pass it back to David, and we can go to the next chart.
Okay. So this is kind of summarizing a little bit of what both Doug talked about and what Mike just talked about. So the way we set up the architecture, we're trying to get the Orion and service module to the lunar vicinity, and so that's where the Orion and service module, as they have been designed, weigh in at about 27 metric tons. And so our initial SLS version, Block 1 version, that's the one that's out on the pad today, or out BAB, I guess at this point, has enough performance to just take the Orion and service module to lunar vicinity. And then as we get into our Block 1B version, which is scheduled to come online here in a couple of years, it has a larger upper stage, the exploration upper stage, and then it's actually designed to take Orion and the service module plus at least 10 metric tons of additional payload with us. So it becomes a little more efficient to bring the things with you, the habitats, the logistics modules, all of the different pieces that of things that you're going to want to work on while you're in that lunar vicinity. And it kind of ties back into what Doug was showing at the beginning. It kind of shows why we didn't use some of the other options, because we would have, once you've settled on where you're going and settled on what you're trying to take there, then you end up designing a rocket that is that takes you there and gets you up and out of the Earth's gravity well, and allows you to do your lunar operations.
I think next we're going to turn it over to Doug to talk a little bit more specifically about the lunar aspect of this and how SLS and the Artemis architecture will support lunar activities and then future Mars missions. And also, if you could touch a little bit on, the question that a lot of people ask. We went to the moon before. We didn't have a lunar gateway. Why do we need one now? Wouldn't it be cheaper and easier if we went back to the moon without it?
So, Kristen, I think we have, I think Mike had one more slide to.
Oh, did we? Okay, I thought
he
had jumped ahead and done too. Okay, sorry about that.
Oh, all good.
No worries. I'll just briefly go through this, but so there are different reentry vehicle designs, and when you look at an architecture that addresses the difference between returning at the low Earth orbit conditions versus lunar or Mars return conditions, as you see in the center of this chart, you need to take into account, as was highlighted before, the amount of energy that you're taking out of the system. So you put all this energy in through the launch vehicle and the launch system, but when you come home and you hit the Earth's atmosphere, you need to take that energy out. So all that chemical energy that was put in at launch, all that smoke and fire you see, needs to be taken back out, and it's still there in the form of kinetic and potential energy. And when you are in low Earth orbit, you're coming back at entry interface at about 17,500 miles an hour, or at Mach 25. and that's your kinetic energy state, and your potential energy is far lower. It's at roughly 250 miles when compared to lunar return. When you come back from the moon, you're coming back at over 24,000 miles an hour, or about Mach 32, and you're coming from a far greater distance at about 250,000 miles. So what that equates to is from low Earth orbit, you need a heat shield capable of protecting you up to temperatures at about 3,000 degrees Fahrenheit. But when you come back from the moon, you need a heat shield capable of protecting your spacecraft and your astronauts of about 5,200 degrees Fahrenheit. I'll just pick on one example here. I'm familiar with the Space Shuttle Orbiter. I worked that program. The orbiter's wing leading edge system was the hottest point, as well as the nose cap was the hottest point of the vehicle. And during a normal reentry, you would see temperatures at about 1,850 to about 2,200 degrees Fahrenheit. And that system was designed to protect that vehicle from those temperatures coming back at a low Earth orbit set of conditions. But the Apollo capsule and the Artemis capsule, in our case, Orion, come back far faster, far hotter, and use a different heat shield design, both from an aerodynamic standpoint, but also from a material standpoint. The material is an ablative, and the ablative material is designed to literally protect the underlying structure and to transfer the heat away from the vehicle. So the ablative material literally melts away, exposing underlying material that is more ablative, and slowly over time transfers the heat away from the vehicle rather than transferring it into the structure. So aerodynamics and the amount of energy in the system is again a key consideration when bringing astronauts or cargo home that need to be baked into it. And that's why there are some differences between a low Earth orbit architecture and a lunar or deep space architecture. So with that, I'll pass it on to Doug for the next chart, please.
Yeah, so we've talked about the requirements in what is needed to obtain our objectives. When we look at roadmaps to the moon and then on to Mars, important aspects of those are in-space propulsion. In this case, it's shown as exploration upper stage, which is in space, you want to get as efficient as possible. Most of the mass that you launch from Earth to go to Mars, for instance, is fuel. So you want a very highly efficient in-space propulsion system that doesn't use a lot of fuel. And I know NASA is now looking at nuclear thermal propulsion, which is about twice as efficient as hydrogen engines. But the Orion capsule is important. Getting to the Block 1B and Block 2 for SLS will be important so it reaches its full potential. In-space habitats are important for the trip to Mars. That can be enhanced by doing testing and demonstrations at a gateway. Initially, you asked about the gateway. Initially, I guess the first mission or two will not employ the gateway, but it's kind of a chicken and egg thing. To go for single missions to the moon, you can go pretty much directly, but as you develop a more robust exploration and in-space economy, it can provide a staging location. It could become a staging location for Mars. You could test habitats that will be used at Mars. So all of these need to be understood in terms of the exact performance and the technical contributions to the architecture. Next chart. And so this is just an artist rendition of the moon, and it shows at least initial operations of what you might do at the moon. It'll be important to place hardware on the moon that will help for a sustainable lunar operation. And that includes things like habitats, it includes power generation, it includes prospecting for propellants or other minerals and processing them. But we have to have the transportation infrastructure in place and understand what these elements are so that we make sure that what we have for transportation does what's needed to get them there. The next chart, please. And so this is a little a next step potentially, and it has to do with an opportunity in 2033 using hardware that's either in development or near in development for the possible flyby mission of Mars in 2033. Because of the planetary relationships between Mars and the Earth, every 15 years there is an opportunity to launch from Earth, fly by the Mars, and have what's called a free return, which means that it comes directly back to Earth with no propulsion to propel it back. You might have to do some adjustments, but it is a free return, so it is much less in-space infrastructure to do this mission. But it would be an exciting first step in getting to the vicinity of Mars that will help motivate follow-on missions to potentially a Phobos mission, one of Mars' moons, and for an eventual Mars landing. Each step of those requires more infrastructure and gets a little harder. So this one mission is an opportunity for in an achievable time frame that could be the first step toward Mars. Can we go to the next chart? And so, as I mentioned, this could then lead to orbital mission to potentially Phobos, where you could do science, get samples and that sort of thing. And then when we get to Mars, we'll have similar infrastructure needs in terms of habitats, surface propulsion, power, and so on in exploring Mars. So the moon can set the stage for this, and the infrastructure that we build and launch infrastructure needs to support our long-term vision. So that's what this represents. Next.
And I'll take this one. Is Doug had just highlighted that the architecture needs to support the needs of getting to the moon, but it could potentially have other applications, whether it's supporting Mars missions or other science or interplanetary missions. In either case, in order to get there, you need enough performance to get out of the Earth's gravity well, achieve that point of trans-lunar or trans-Mars, or just the ability to escape the Earth's gravity well, and then transit out to whatever your target mission point is. But you also need to have the volume and the capacity of the vehicle to get you there. So not only do you need cargo volume, but you need performance. In order to get there, you've got a couple of options. You can do a lunar gravity assist using different orbital bodies that takes you a longer period of time to get out there, or you can basically do a direct mission. And a direct mission requires higher performance. The spacecraft itself needs to be capable of handling that direct transfer because it's a higher energy transfer than a lunar gravity assist. But by taking less time, you have more time to perform your primary mission, and you don't spend months or years transferring out to another orbiting body. But you also reduce your risk in that transfer time. It's less wear and tear on the vehicle. It's less exposure to the deep space radiation environment. It's less exposure to the micrometeoroid environment. And those are cumulative risks. The longer you spend in that time and transfer, the greater your risk to your primary mission is. And the solar system is a really big place. The moon is about 250,000 miles away from Earth. Mars is about 250 million miles away, so months away from Earth. And then Jupiter and Saturn are 600 million miles and over 1 billion miles away. So when you start taking into account these distances, not only are you accumulating time, but you're accumulating risk to your mission. And those are things that are factored into the overall, whether it's science mission or human exploration mission, as part of the architecture. So with that, I'll pass it to Dave for the next chart, please.
Okay, I was just going to run through a couple more thought processes on that and why you want to go do some of these things. So the interesting thing is the most likely place for life within our solar system outside of our planet is on some of the icy moons of Jupiter and Saturn. And as Mike was just pointing out, it takes a long time to get there. So one of the things that as we're getting all of this infrastructure in place for Artemis, it opens up a lot of opportunities for science missions to go out and explore some of these things. So one of the examples is if I'm going to the Jovian system with a smaller rocket, it will take me at least 5, if not 7 years to get there. Whereas I can go with even an SLS Block 1, and I can get to Jupiter in about 2 years. So you start thinking about how much faster I'm getting the science back and able to factor that in and then take the next steps and do even more science in those areas. I'll go into the next chart and go with some other, oh, excuse me, voice is giving out. So some of the other things that you can do when you have really this kind of a capability of putting up a large mass and the velocity that you can get out of these systems. So if you're wanting to go and do planetary protection, the whole key behind planetary protection is to get to a rogue asteroid as quickly as possible, because the further out you are, the more of a lever arm you have, the less energy you have to put into it to deflect it. And the more mass you have taking out there, the better your chance of being able to deflect it. Let's see, exploring the interstellar medium. We've been looking at some missions to an interstellar probe mission, and with some configurations that we've been looking at, you can actually get to the interstellar medium in about 15 years. So that's, if you remember that graphic we had of the Earth's magnetosphere, and the sun has a similar heliosphere. And so that's actually getting beyond the heliosphere in about 15 years into interstellar space. And it would actually be able to catch up and pass the Voyager 1 and Voyager 2 spacecraft in 15 years. So looking farther in distance and further back in time, that's actually talking about even bigger reflectors than James Webb. When you start getting up in the range of an 8 meter or so monolithic reflector, or a little bit larger than that with a segmented reflector like the Webb telescope, you can actually start doing spectroscopy on atmospheres of exoplanets and determine whether we believe that there's life on some of those planets that we're seeing around other stars. And then the other thing is just discovery science at the far reaches of the solar system. It's, as when we went out to Pluto, it was not what we were expecting. And so, when we go out and we look at things, it's not always I'm going out there to go answer these 3 questions. Sometimes it's things that you just didn't expect, and you learn something completely new. And we can get there sooner and look at things and make those discoveries a lot quicker than we could before we put this infrastructure in place. And I think that was next chart.
I think that wraps it up. We ran a little bit over. We apologize. For those of you who have questions, please jump in on the chat.
Kristen, if I might, I missed a question that you asked that I think is important. You asked about why we go back to the moon while you're dialing up the next ones. Actually, through obtaining all the objectives and the processes that we went through, there are a lot of things that scientists are still interested in learning from the moon. Being our closest neighbor, it represents the same history that our Earth has gone through. It has much more dramatic landscapes than Apollo landed in. There are resources there that we need ground truth on, that we have orbital information on, but it is an opportunity to prepare for Mars. So there's a lot to do at the moon. And I didn't want to pass up that question. I'm sorry.
Appreciate
Yeah.
you bringing that up. I don't see any questions on the chat, so I guess please jump in. But oh, it looks like we have one. We have one here. Recently, the planetary decadal recommended a flagship level mission out to the 7th planet in our solar system, and to do it fast. They recommended that the ship be designed with current technology to speed things along. What are the chances that SLS would be employed to get the mission out there faster? Has SMD reached out to you, or do you see them reaching out? Thank you.
I guess I'll take a crack at that one. I'm not aware if that SMD's reached out to use the space launch system or not, but typically what the process is that we'll look at what the requirements are of the mission, and a trade study will be done, and then there will be some vetting of what options are in play. So I'm not aware of anything that's out there, but if there was something, then it would probably take some number of weeks to go through that. I don't know if anybody else has anything to add on that one.
Yeah, I mean, I can add some, because I've seen some of the interactions that have been going on with other programs. So generally speaking, what I've seen is folks in the Science Mission Directorate or folks at JPL or Johns Hopkins APL or whoever will reach out to the Marshall team, the NASA folks at Marshall, and ask them about the capabilities of SLS and how that can be applied to their missions. And I know that there have been some initial discussions on some of those missions that just came out of the planetary decadal, but I don't know how far along they are.
I have a question. I think we've addressed this in one of our previous media webinars, but it comes up all the time. I know I personally get asked it all the time, and you all touched on this a little bit when you talked about the amount of fuel needed to go to a mission to the moon. But can you touch a little bit more on reusability? And it's a question. Whoever wants to take this one, but why SLS isn't a reusable rocket? Why NASA didn't decide to try to go with a reusable rocket for going to the moon?
I can take a crack at it, Doug. You may have more background than I do on some of this. I haven't been on the program as long, but I would characterize SLS as a performance optimized system. You are trying to get as much performance out of the system as possible to deliver crew and cargo to the point of translunar injection. There are various trade-offs associated with that, and reusability of components is definitely one of them. If you want to hold back some of that performance to have reusability, that's a consideration, and that was something that we chose to not do with SLS. I don't know, Doug, if you have anything to add on that one.
Yeah, I can add a little. When we made the SLS decision, our budget was very squeezed, and we primarily had to use good systems. The solid rocket boosters, we'd already tested the 5-segment booster, and we had the shuttle main engines, which are still right at the top of technology in terms of hydrogen engines. we did not have, we had to get on with it because we had people working on the program, and that is a big design issue when you're starting from where we were. So that was really not in the cards at that time. That's not to say that it can't be looked at for potentially saving the boosters or saving the engines as we did in the shuttle, to see if that's practical. It gets harder on a larger scale to reuse a launch vehicle. So that's my background on it.
I'll just add one other simple point when we were talking about the velocities that you're going as well. Is this, you know, this rocket really likes to fly. So if you think about where you normally would drop off the core stage of other rockets, that it would end up in the South Atlantic. Well, this one has enough energy that it's going all the way around, and it's going to land in the Pacific, you know, near the Hawaiian Islands. So it really likes to fly. It's got a lot of energy, which means that it makes reusability more difficult because you're coming back at faster velocities and more heat, just like Mike was talking about with the reentry on the on the Orion capsule. And I would like to point out that the Orion capsule is reusable, so it's not that there's not reuse in the system. So.
Well, do we have any, we're getting close to time. Any other questions here that we have? Or Frank, did you have any questions you wanted to ask?
Going once, going twice. Maybe I'll take us in right now, but so I want to thank the participants here today, both the audience as well as the presenters. A lot of work went into putting this together, and a lot of experience went into this together. I think cumulatively, you guys probably have close or maybe a little bit over a century of experience, so a lot of thought went into this. And this is as this is the 5th. We've got a 6th coming up next Friday, May 13th. It's going to be verification of advanced launch vehicle designs by ground test. Now, that may sound boring, but in fact, you got to think to yourself, look at all the work that's been going on so far. We've done burst tests, done wet dress rehearsals. We're in the process of doing wet dress rehearsals, green run. We're going to talk about all those types of things that are needed in order to validate the design before you put a rocket on the pad and launch it actually into space. That's going to be done by the Jacobs Space Exploration Group at NASA Marshall Space Flight Center in Huntsville. We've got Tim Sanders, who's the director for test operations at Jacobs, and Lisa Bates, who's the director at NASA Marshall Space Flight Center Test Lab. So look forward to the audience next week, or the program next week. Again, thank you all for coming, and this will be archived in a day or two on our website if you have any follow-up questions. Thank you very much. Have a great day.
Thank you all.